Hello everybody. Today we're going to cover chapter 14 from your book, which is on groundwater. So, groundwater is one of the most important and also one of the most widely available resources to us. Yet, people's perception of the subsurface environment from which groundwater comes from are typically unclear and incorrect. So this is probably because the groundwater environment is largely hidden from the view of us humans. And this is only really seen in places like caves or mines where we do have some groundwater and we can get to. And it is in these large openings like caves and mines that tend to contribute to the people's misconceptions about the groundwater work. So typically, groundwater in caves and mines will flow as a channel that appears to have cut through and that is now on top of the rock for the most part. And on a common basis, people tend to also base their observations that rock is for the most part solid and for the most part impermeable. So both of these things combined, our observations at caves and mines of channels flowing underground and the fact that we believe that rock is solid and impermeable, make people have a misconception that groundwater flows as rivers underground or as big channels. However, for the most part, this is not the case. In truth, much of the rock is in fact not completely solid and not impermeable, as we know now. And it does in fact often contain a lot of pore spaces or empty spaces, which is what pore spaces are. So these empty spaces appear in between the grains of soils and sediments. And many of the rocks that don't have grains, but rather a more crystalline structure to them, will have a lot of narrow joints and fractures within the bedrock, making it available for these pore spaces to occur. So in fact, rock is not necessarily solid and impermeable, but is rather a phase in which some liquids and gases can travel through. So when these empty spaces are added up, the resulting volume that they occupy is actually very large. And so if these spaces get filled up or they get saturated with water that will infiltrate through the soils and all the way to the rock downward, then the water will now be stored as groundwater. So, most groundwater does not flow in underground rivers or channels, as is a misconception, but it will rather flow through tiny fractures and also through tiny pore spaces within the rock sediments, or within the rock and through the spaces within the soils and sediments. When we consider the entire hydrosphere, only about 0.6% is located underground. Once we exclude the oceans and the saline waters and fresh waters, the significance of groundwater becomes more apparent. So we see that groundwater makes up about 30.1% of the fresh water that we have from this graph, and about 96% of the liquid fresh water that we have, so a very large amount of that liquid fresh water. The remaining fresh water lies typically the remaining liquid fresh water lies typically in lakes and in streams, and then the remaining fresh water overall lies in ice sheets or glaciers. So, speaking from an accessibility perspective, groundwater represents the largest reservoir of fresh water that is actually available to humans. So the value that it has for human and for economic growth is actually huge. It's incalculable. So groundwater is also very important because it's a huge erosional agent. So by dissolving or through the dissolving action of groundwater, it will slowly remove soluble rock such as limestone, like we saw in chapter 7 and in chapter 6. And this allows for surface expressions such as sinkholes or tower karst to form, and we will look at later in the lecture. Another sort of features that they form are underground caverns, which are just spectacular representations of groundwater's erosional work. So again, we'll cover all of these towards the later part of the lecture. So much of the water that flows in rivers is actually not direct runoff from rain or from snowmelt. Most of the running water was initially water that infiltrated into the soil and bedrock to flow slowly and eventually will move towards the surface and join stream channels. So again, much of that water that precipitated, infiltrated through the ground, made it as groundwater. That groundwater flowed really slowly through the soils and through the fractures and eventually got incorporated back into a stream. So this causes groundwater to be a storage that will sustain streams during many periods of time, even during dry periods. And we'll see the mechanism for this in a few slides as well. So water, as you know, is very basic to our lives. We need it, as do many other species within the earth. Each day in the US, for example, we use about 306 billion gallons of fresh water. According to the USGS estimates, 75% of this comes from surface water, and the remaining 25% from this use of water comes from groundwater sources. So one of the convenient aspects of groundwater is that it almost always will exist anywhere within the country at some depth, even in places that are typically dry and can't rely on the readily available fresh water from lakes or streams. So we are able to reach this groundwater, as some of you know, by withdrawing it from a well that is placed in the ground. So we pump the water upwards through the well, and said water will flow through the pore spaces and the fractures in the nearby areas of the well and eventually make it through the well and up to the surface where we use it. The primary ways in which we use groundwater, at least here in the US, are by four main uses. And the first one is irrigation. So this is going to use the greatest portion of the groundwater, which is about 71% again, and most of this is used in the western states, which typically receive a lot less precipitation than the eastern ones. And so 42% of the water that we use for irrigation is from the underground storage in the western states. Okay? Another 25% of the groundwater used in the country is to public and domestic uses, which include water for indoor and outdoor households and whatever purposes they may have, as well as water for commercial uses. So water used for indoor purposes is anything from cooking water, showering, dishwashing, washing your clothes, and flushing the toilets and things like that. As you can see from the image on the lower right over here, the greatest amount of gallons of water used go into flushing the toilets. So, I thought that was a little bit concerning. So, since I looked at this graph, what I started doing at home is using less of my toilets, or I should say, flushing my toilets less. So, I encourage you to do the same. It might be a little bit gross at first, but for the most part, you should follow the saying of if it's yellow, let it mellow. If it's brown, flush it down. This is to reduce our water usage, and I encourage you to do it. Another thing you can do in order to reduce the amount of times that you're flushing the toilet is collect the water that you use for showering and using that water to flush the toilet. So if you collect that water in a bucket and then you pour it down the toilet every time you pee or you poop, then whatever contents there were will flush away without using any extra water. So any outdoor uses are things such as watering the lawns and gardens. So people who obtain their water from a private supply, for the most part, are going to be from groundwater. So, and when I say for the most part, I mean 98% of people who, again, get their water from a private supply is going to be from groundwater. The remaining 6% of groundwater use overall in the country goes into the industry, mining, livestock, aquaculture, which is basically fish hatcheries, a lot of industry operations such as manufacturing and drilling operations also take up a lot of water, and so it makes up a fairly large chunk of the groundwater usage in our country. So when water precipitates from the atmosphere, it can either become runoff, it can be stored as ice or snow, it can return back to the atmosphere by evapotranspiration, or it can either infiltrate or percolate as it gets soaked in through the soils, and if it infiltrates all the way down through the rocks. Whether the water does one or another thing is highly dependent on many factors, which we already looked at a little bit on the lecture for the last chapter. So again, the precipitated water will either infiltrate or run off based on 5 different factors. The first one is going to be the intensity and duration of the rainfall. The second one is the amount of water that is already in the soil, so the amount of saturation. The third one is the nature of the surface material. The fourth one is the slope of the land. And then the last one is going to be the extent and the type of vegetation where the precipitation occurs. So for some of the examples of how these 5 factors are going to influence whether the water becomes runoff or it infiltrates, go back to lecture on chapter 13, and there I talk a little bit more about the different examples. All right, so now we're going to talk about the water table a little bit more and the different zones that make up the depths at which water lies or does not lie. So some of the water that actually gets soaked into the ground does not travel very far. It doesn't actually infiltrate, it just merely percolates. So this water is not able to infiltrate because it is held by the molecular attraction as a surface film on the soil particles. This zone is called the zone of moisture, and as you're seeing it here, it only lies in the top part as you're going deeper within the earth. So it is typically this soil moisture zone that plants use for intake through their roots. And it is also most of the water that the plants take from the zone that gets evapotranspirated back into the atmosphere. The water which is not held as soil moisture will flow downward through the pore spaces and fractures until it reaches a zone in which all the pore spaces are filled with water. This zone is called the zone of saturation. So they're going to flow all the way from here through this space and get basically deposited here in a place where all of those pores are saturated with water. So the zone is called zone of saturation. We also refer to it as phreatic zone. And any water found in this zone is considered to be groundwater. The upper limit of the zone is called the water table. So you're seeing it right here. And a bit upward from the water table is something called the capillary fringe. So capillary fringe is where the water is held by surface tension in tiny passages between grains of soil and sediment. And so it's an area right before water actually fills in the pores, and it's just simply held by, again, surface tension. It's a little bit more complex, but as long as you know where the capillary fringe lies, I'll be happy. The area in between the water table and the zone of moisture through which the water flows downward, and which includes the capillary fringe, is called the zone or the unsaturated zone, or also referred to as the vadose zone. And in this zone, although there is water that is flowing through the pores and sometimes occupying part of the pores, it cannot be pumped as it is actually clinging too hard to the grains that it surrounds. By contrast, in the saturated zone, there's actually enough pressure that has been built up for water to readily enter the wells and then be further extracted when we pump it out.